We will now discuss the fundamental theory derived in our undergraduate mechanics course, which is called Engineer's Beam Theory, or in other words, Flexure Beam Theory. Before starting any theory, it is important to appreciate the assumptions based on which the whole theory has been formulated. The assumptions of Engineer's Beam Theory are as follows. Plane section remain plane, material is homogeneous and obeys Hooke's law, modulus of elasticity for compression and tension are equal. Beam has got constant cross section and is straight initially before application of the load. And finally, the plane of loading must contain a principal axis of beam cross section, and loads must be perpendicular to the longitudinal axis of the beam. In all these, the most basic assumption is assumption number one, which is plane section remain plane. This is the backbone of reinforced concrete theory of beams and steel design of beams. This assumption says that a beam cross section, which is a plane, will remain straight after bending. We will see that using this assumption, the calculations become very simple and we get a very simplified form of Flexure formula. The engineer's beam theory is good for ordinary beams which have got cross section very small as compared to the length. If we have structures such as deep beams or walls, then engineer's beam theory gives us wrong answers. It is those structures for which we will be developing the theory of elasticity. The second assumption, which is material in beam is homogeneous and obeys Hooke's law, has been touched upon previously. We discussed that the stress equation is derived for a body which is homogeneous. Homogeneous meaning that body is continuous and cohesive. Continuity of a body means that there are no cracks or gaps in the body. The body has got a uniform surface. Cohesiveness, on the other hand, means that the molecules making up the whole body are uniformly distributed around the body. The molecular structure has got no gaps or no voids. The whole structure is a solid mass. Stress is equal to E times strain is another assumption of engineer's beam theory, and we have already discussed how stress is equal to E times strain is important for different bodies. The third assumption is that moduli of elasticity for tension and compression are equal. So, like steel, we have the modulus of elasticity both in tension and compression the same. Assumption 3 can be adjusted to, to meet those materials which don't have modulus of elasticity in tension and compression equal, such as reinforced concrete. In reinforced concrete, we have got a compression section, which is normally concrete, and a tension section, which is steel. And both concrete and steel have different modulus of elasticities. So we tailor the engineer's beam theory and make it suit to the RC beams. Assumption number 4, beam is initially straight and having constant cross section. Now again, assumption 4 can be adjusted for those beams which have got initial deformation and those beams whose cross section area is variable. In other words, engineer's beam theory can be adjusted to get around assumption 4. Assumption 5 says that the load applied should be perpendicular to the longitudinal axis of the beam. Longitudinal axis is that axis which is along the span of the beam. Also, the load should be applied at the centroid of the beam so that there isn't any twisting. Assumption 5 will be further discussed and elaborated shortly. As I said, assumption 2, 3, and 4, they can be adjusted if they are not getting satisfied. Assumption 1 is that assumption based on which the whole theory lies. And we can't relax assumption 1 in the case of engineer's beam theory. And we will see now in the derivation part that how assumption 1 make the calculations very easier. Let us now move on to derivation of Flexure formula. A simply supported beam which is subjected to some loading. Let us consider two adjacent sections AB and CD which are at very small distance x3 apart. We assume that the x3 is along the length of the beam and x1 and x2 are along the plane of the beam. After application of the load, the beam will bend. Imagine we take a portion of a beam. This portion clearly shows that AB and CD have moved. The BD has moved apart, where AC has moved closer after application of the load. Based on our assumption 1, AB and CD stays straight. They don't become curvy or they don't become jagged after application of the load. This assumption will only be valid if the cross-section area is very small as compared to the overall span of the beam. If we keep on increasing our cross-section area, then there is a possibility that our cross-section might become jagged. If we assume that AB and CD are extended to meet at point O, and then keeping O at center, we can draw a circle having a radius rho. Thus, EF can be a sector of a circle. EF is very close to each other. In other words, EF is very small to be considered as an arc of a circle. In general, the neutral axis is a parabolic curve. There is a difference between centroidal axis and neutral axis. Centroidal axis is a line which is passing through a point about which the whole weight is considered to be concentrated. On the other hand, neutral axis is a line about which total force is considered zero in any body. So if AC come closer to each other and BD goes further apart, then that means there is a region which is under compression and there is a region which is under tension. Then there must be a point where the section changes from compression to tension. And at that point, the force would be zero. Neutral axis is actually that line about which total force is zero. Imagine we are interested in finding out the extension of a fiber which is located at a distance x2 from the neutral axis. So we draw a line C prime D prime which is parallel to AB, and then we consider that OD is a transversal between two parallel lines AB and C prime D prime. That makes the angle subtended between OE and OF d theta equal to the angle between F d prime and D. We assume that the GH fiber is extended by HK. So in order to find out the extension of HK, we have to do some mechanics. As we discussed, that strain is change in length by original length. So for GH fiber, the change in length is x2 d theta, remembering that S is equal to r theta. That is the deformation. The original length, which is EF, that is rho d theta. Remember that EF is the fiber where no force is applied, or that is a neutral axis. So therefore, EF and GH are equal. Thus, plugging value in the strain equation, we will get the strain in the fiber GH. After this, we can multiply the strain with modulus of elasticity and get stress in GH fiber. Using this stress value, we can find stress at any fiber located within the cross section of the beam. In this lecture, we will be considering only those bodies which are at rest. We are not considering any dynamic effects on bodies. So we assume that the current body is also at rest. Under this consideration, we have to say that there are six equilibrium equations which must be satisfied. And those six equations are summation of forces in all the directions and summation of moments in all the direction must sum up to zero. Imagine that we take a small portion of this beam. This is an element of the beam having an exploratory surface. This element is in the form of a cube, i.e., it has got six sides. Please notice that we have got a neutral axis, we have got a neutral surface, which is the surface containing neutral axis, and that is in x1, x3 plane. We have got the loading plane, which is the longitudinal plane x2, x3. This loading plane is perpendicular to the neutral surface. Since we are dealing with the mechanics problem, so we have to work out the internal effects. As we discussed previously, the internal effects are either forces or moments. In this cube, we will have forces on the surface of the cube. Distinctively, we have got three different types of forces. One is the force which is parallel to x3 axis, and two are the forces which are lying in plane axis, in the plane area axis and x1, x2. So we have got one stress which is out of plane and we have got two stresses which are in plane. Since this cube has got six faces, so at every face we will have three stresses that will give us 18 stresses altogether. Later we will see that these 18 can be broken down, can be brought to nine distinct stress components. Imagine our our exploratory surface is the one which has got the outward drawn normal in x3 direction. One thing we must have realized that in order to define a stress, we would need what phase we are talking about and what direction of force we are talking about. These two parameters will determine the stress component. So if we are talking about our exploratory area, which has got outward drawn normal in x3 direction, this would have axial stress 3 facing in x3. The first subscript of the stress means the outward drawn normal of the surface on which this stress occurs. And the second subscript means the direction of the force which is responsible to create that stress. So now stress 3-1 would mean that we are talking about exploratory surface 3 having outward drawn normal in x3 direction, and the stress is resulting from a force which is in the direction of x1. Similarly, stress 3-2 would mean the same exploratory surface with a force applied in direction x2. Please note that on every surface we have got two shear stresses and one axial stress. We divide the whole area into very small areas of dimension dA. So this whole exploratory section is made up of infinite small differential elements of dimension dA. Let us assume that we consider one small area element which is located at a distance x2 from the from the neutral axis and x1 from the x2 axis or the longitudinal plane. At this element, we have axial stress, which is stress 3 times dA, and we have got two shear stresses, which is shear forces, which are stress 3-1 dA and sigma 3-2 dA. Now, let us apply the equilibrium equations. We start with the first equation, which is summation of all the forces in F3 direction must be equal to 0. This equation is saying that the externally applied forces must equal to internally applied force. The externally applied forces are 0. There is no external load applied in X3 direction. So we get 0 on the right hand side. On the left hand side, which is the internal effect, that we can write as sigma 33 times dA and put an integral sign having area as the variable. So that means that our small area dA time sigma 33, which is a force on differential element dA, those have to be summed up for the whole cross section in order to get the average force in the direction of x3. Sigma 33 has been derived as ex2 by rho. So plug and jug and we get ex2 by rho dA. Now E and rho, E being the modulus of elasticity and rho being the radius, they are constant for any cross section. Please note that any parameter which is not changing with area can be brought out of this integral sign. Modulus of elasticity being the property of the material is not changing with the cross-sectional area, so that can be brought out. Rho, which is the radius at which the neutral axis bends, that is constant for a particular cross-section. Rho does change as we move longitudinally, but rho doesn't change when we are moving along the cross-section area. So therefore, these both are brought out. Now we are left with x2 dA inside the integral. dA will stay inside the integral because it is an area dependent integral. x2 is the dimension along the cross section. So again, it contributes to the area. That's why it can't be brought out. If we look closely into this equation, x2 times dA is the moment of the differential area about the neutral axis. Now, this whole equation has to equate to 0. We can't have E by rho equal to 0. So, undoubtedly, x2 dA integral is equal to 0. And that is actually the first moment of area. This can be written as AX2 bar. Please note, x2 dA is the total moment of area. This is also called first moment of area. Only x2 bar in this relation can be 0. We conclude that the distance from the neutral axis to the centroid of the cross-sectional area must be 0. In other words, neutral axis must contain the centroidal axis of the cross section. So this equation, which is x2 dA integral, that is actually the definition of a centroidal axis. And based on that, we conclude that neutral axis contains the centroidal axis of the cross-sectional area. Now let us consider the second force equation, which is summation of F2 is equal to some applied load. F2 are all the forces which are in x2 direction, and we have already discussed in the assumption that loads are applied only in the loading plane, which is this x2 x3 plane. So if the load is applied in this plane, then we have the again the external force equal to the internal force. But at this time we would have the right hand side not equal to 0 but equal to overall applied load in the x2 direction. And that's why summation of F2 is equal to either P or V, whether we call it shear or we call it the applied load. Please note, sigma 32 is in the x2 direction, and sigma 32 times dA integral must be equal to the applied load, and that is the definition of shear. Finally, we discuss the summation of moment about x1. The moment about x1 which is the neutral axis, is equal to applied external moment. And hence, this gives us the Flexure formula. So, the internal force resisting the external moment is sigma 33 times dA into x2. This will give us the moment equal to sigma 3 into x2 dA bracket. Plugging the values of sigma 3 will give us x2 square dA inside the integral bracket and E by rho kicked out of the integral bracket. X2 square dA is actually moment of inertia. So this is the area of moment multiplied with the square of lever arm or second area of moment. This is also called moment of inertia. Please note, if in our cross section the x2 is made bigger, then moment capacity of the cross section can be increased. So in the case of I cross section, the flanges are placed at some distance from the neutral axis, and that makes the cross section capacity higher. So if we are interested in a higher cross section capacity, we take that I section whose distance between the flanges is higher. Cross sections such as plate girders gives us very high moment capacity. In contrast, if we bring both these flanges together, we will have a cruciform cross section, and this cross section is very inefficient because the lever arm x2 bar is very small for the flanges. From all this discussion, it is clear that the flanges are responsible to take our moment, or in other words, to give us the moment capacity. And the web is responsible to take our shear.